Hello and welcome to lecture 48. We are discussing about the recent advances in turbofan engines. In last lecture, we were discussing about the military engines, in which specifically we have mentioned about F135 engine, and we also have discussed about the variable cycle engine. And very importantly, we were discussing about what all we mean by the generation of aircraft engine for military purpose. Say generation 3, generation 4, 4.5, 5 and 6 generation aircraft. So here if we look at say F135, we can say that's what is coming under 5th generation aircraft, and for future coming engines it will be the 6th generation aircraft. That's what is called variable cycle engine. As we have discussed, a lot of research, that's what was been started in 70s, and now we reach to the state where those logics, that's what will be implemented and that will be come out as a product. And do not get confused in terms of cycle. As we have discussed, this is nothing to do in terms of say thermodynamic cycle. This is what is with the operating cycle. It means it is say turbojet cycle and turbofan cycle. So we would like to have benefits of both turbojet engine. We know what is the benefit of turbojet engine. We are looking for higher thrust, and in terms of turbofan engine we are looking for fuel economy, and for the future generation aircraft we are looking for both as our requirement. Now let's move towards the next. Say this is what all we were discussing in terms of turbofan engine, where we are having say fan or fans. It depends on what is the kind of configuration we have. We may be having these engines to be high bypass ratio engine or low bypass ratio engine. You have all idea now. Say here in this case we know our HP turbine, that's what is used to rotate the HP compressor, and LP turbine, that's what is used to rotate both LP compressor as well as the fan. Now in terms of thermodynamic cycle, we have represented this cycle. Let's look at the ideal cycle. There is a specific reason behind selecting this. You will realize very soon. Say process infinity to 2, that's what is representing my intake, and here in this case this is representing my compression work, ideal compression work in fan. This is representing my work in say our compressor. Then 3 to 4, that's what is representing compression process in say HP compressor. 4 to 5, that's what is representing my heat addition process. 5 to 6, that's what is representing HP turbine work. 6 to 7, that's what is representing our say LP turbine work, and 5 to 9 or 7 to 9, that's what is representing my exhaust configuration. So this is what all we know in terms of our thermodynamic cycle for turbofan engine. So in this, let's try to understand and let's try to do some modification in order to achieve our expectations. So when we say what we are looking for is in terms of improvement of thermal efficiency, improvement of propulsive efficiency, improvement of overall efficiency, lower specific fuel consumption, all those terminologies you are aware of. So let's try to target those one by one. Suppose if I say we would like to improve the thermal efficiency, we know in order to achieve higher thermal efficiency we are looking for higher turbine entry temperature, and in terms of achieving say higher thrust we are looking for this turbine entry temperature to be higher. Similarly, we have discussed about higher overall pressure ratio configuration also. Let's try to look at in a different way. Can we achieve higher thermal efficiency without increasing the turbine entry temperature? We will say, is it possible? Yeah, let's try to explore that kind of possible. Let's try to learn in a different way. Suppose if I consider here, say this is we have turbofan engine in which I am adding the components here. This component I am representing as a intercooler. Now this intercooler, it's a heat exchange device, or we can say it's a heat exchanger, where the exchange of heat, that's what will be happening. So hot fluid that will get cool and cold fluid that will get hot. Now the question will arise, what is the meaning of heating and cooling in our engine and why are we putting this kind of configuration? So let's try to understand in terms of our thermodynamic cycle. That's what is represented on TS diagram. So here in this case, suppose if I consider this is my atmospheric pressure, this is representing my intake configuration. Now we have from 2 to 2A, that is representing the compression work which has happened in the fan. From 2A to 3, that's what is representing my LP compression process. So here in this case, so if we try to look at some portion, or say here if you look at from here, we have taken out our air and we are permitting that air to pass through this device, what we call intercooler. What will it be doing? We know because of compression our temperature will be higher, our pressure will be higher. Now we will be trying to cool down that high temperature air which is coming out from LP compressor by using this bypass air. So what will it be looking like? So here if you look at, this is representing my ideal process from 3 to 4i, where I am not having intercooler. Suppose if I am incorporating this intercooler, so what will it be doing? Here if we look at the process, it is say from 3 to 3c, that's what is representing the cooling process. That's what is happening ideally, we say, at constant pressure. So what exactly it is doing? It will be reducing the temperature of the air which was coming out from LP compressor. What is happening here? Say here this is representing my exhaust from the bypass duct. The amount of heat that will be liberated or that will be given away by this hot air, that will be taken by this cold air, and that's the reason why the temperature will be increasing from 2A to 10. Now this low temperature and the same pressure air, that's what we are inputting in our say HP compressor. This compression process, it is represented by 3C to 4. Now the same air, that's what will be enter inside the combustion chamber and it will be raising the temperature to say 5. Suppose we consider for ideal cycle without intercooler and with intercooler, my turbine entry temperature, that's what is same. Process 5 to 6, that's what is representing my HP turbine work. 6 to 7, it is LP turbine work, and this 8 to 9, that's what is representing my nozzle expansion work. Now the question will arise, what exactly we have done? Can you start thinking of what we are doing here? Say from pressure station 10 to 11, that's what is the exhaust from my fan. What exactly are we doing? So here if we look at carefully, this is the shaded region we are getting additional. What is the meaning of that? This area under this TS diagram, that's what is representing my work capacity. So you can say we are able to achieve additional amount of work. Okay. At the same time, let's try to understand. Suppose say if I want to compress my air from 3 to 4i, the amount of work, that's what is required, that's what is 5 to 6. And here in this case, if we look at, this is permitting us to achieve high pressure at low temperature. So that is what is our second benefit in sense. Let's try to look at what exactly we have done. Suppose say ideally if we consider the amount of heat what we are supplying, it is MCP delta T0, that's what is T05 minus T04i. And in the case of intercooler, if we look at this amount of heat required, that's what will be higher compared to my ideal condition. So we can say by doing or by incorporating this intercooling, we are getting the benefit in terms of achieving say additional amount of work. At the same time, since we are able to get the same amount of work done with less amount of say turbine work, that's what will be increasing our exit enthalpy, means we are able to increase our exit velocity and thereby we are improving our thrust. But at the same time, what we are doing, we are putting the additional amount of heat. So amount of fuel requirement, that's what will be higher. So you need to have some compensation in that sense. Okay, so this we say is an intercooler cycle. Now let's try to incorporate one more device. So if you look at carefully what we have done, we have our intercooler here and my high temperature air, that's what is coming out from HP compressor, that's what we are supplying to some additional device here. This device I say as a regenerator, that is also heat exchanger. So what exactly this device will be doing, as we have discussed for the intercooler, similarly here this is working at higher temperature. So the exhaust gas what is coming out from our LP turbine, that is having higher enthalpy, higher temperature. If we will be passing through this nozzle, we are achieving say amount of the expansion work. But if we will be using this for heating of the air which is coming out from the HP compressor, that's what will be raising the temperature of HP compressor air. Now that air if we will be supplying into the combustion chamber, we will be having other story. So let's try to understand what exactly is the meaning of what we have done here. So here in line to what all we have discussed, say we have our intercooler. Now here from 5 to 6, that's what we are representing our HP turbine expansion work. 6 to 7, that's what is representing LP turbine expansion work. Here in this case what is happening, the gas which will be coming out from say LP turbine, that's what we are passing to this regenerator. So my temperature at the entry of the nozzle, that's what will be lower because we have taken away some amount of heat. How we have taken out some amount of heat? Say this is the amount of heat. So what exactly will it be doing? It will be raising the temperature of my air which is coming out from the HP compressor. So here we are having this as a heat exchange process which is happening. And this 8 to 9, that's what is representing our ideal expansion in the nozzle, and 10 to 11, that's what is representing my expansion in the fan. So here if we look at carefully what it says, if I consider I am having ideal condition, my amount of heat input, it is MCP T05 minus T04I. Suppose if I consider with say intercooling as a cycle, this will be T05 minus T04. And if I am incorporating intercooling and regeneration, just look at here, if we observe carefully the amount of heat what we are supplying for intercooler and regenerative cycle, that's what is lower. That means it is improving my thermal efficiency. So now you can realize this also is the possibility in order to address the issues what we were discussing in terms of improving the thermal efficiency. So thermal efficiency can be improved by increasing the turbine entry temperature. It can be improved by overall pressure ratio. This is one of the possibility by incorporating intercooler and regenerator. This logic, that's what was earlier been used for land-based power plant. Later on people they started exploring that for application for the aero engines. Okay, do not get confused with the term of regenerator and reheating. This regenerator, it's a heat exchange device where we are regenerating the heat, that's what is supplied to the combustion chamber. Suppose if I consider say reheater, then afterburner it is called a reheater because we are again or we are heating our gas again. That's the reason why it is called reheater. Okay. Now let's try to understand this what cycle we are discussing in terms of my actual process. So in actual, if we consider this is representing my actual process in intake, this is representing my actual cycle for say fan, this is representing my compression work, actual compression work in the fan. Here if we look at, this is representing my say intercooler work. What is happening, say there will be some amount of pressure that will be dropped within this intercooler, and that's the reason why my pressure point, that's what is lower. You can understand when the air, that's what is passing through any device, because of say presence of solid body, we will be having losses because of friction, and those losses we are considering or configuring in terms of pressure loss. So here this is what is 3C. Similarly, here in the case of say exhaust to the nozzle, I will be having say my temperature to be lower and pressure also will be lower compared to my ideal process. 3C to 4, which is representing HP compressor work. Here in this case, since we are using say reheating process, so my inlet, that's what is represented from the process 4 to 4H. Here this is representing my process of say heating by using say regenerator, it is from 4 to 4H. This is representing the combustion process which is happening inside our combustion chamber, that is from 4H to 5. 5 to 6, that's what is representing our actual HP turbine work. Then 6 to 7, which is representing my LP turbine work, and 7 to 8, that's what is representing what is happening inside our regenerator. And if we look at carefully, there is an exchange of heat which is happening, and that's the reason why we are achieving our say combustion chamber entry temperature to be 4H. And from 8 to 9, it is representing my nozzle work, and 10 to 11, that's what is representing our say expansion work which is happening in the turbine nozzle. So this is what is very interesting and very important case, and like this need to be understood thoroughly. So suppose if I consider say my device as say intercooler, we can say we are having two streams which are entering and two streams that's what are coming out. What are the stream which are entering? Say we are having our core air, that's what is coming out, it is entering inside the intercooler. The air which is coming out from the fan, that's what is entering inside. And at the exit, if we consider say H03, it is nothing but my HP say LP compressor air, that's what will be getting cooled, and here this is representing the heating process. Okay, if we will be doing the energy balance, then this can be represented in terms of MCP delta T0, that is nothing but beta m dot core H010 minus H03A, that is nothing but which is happening inside my fan stream, and here it is representing in my core stream. Similarly, if I will be representing for say generator, we are having the stream which is coming out from the HP compressor, and we have one stream which is coming out from the LP turbine, and that's what will be getting heated up in terms of H04H, and it is getting cool in terms of H08, and this is representing my energy balance for the regenerator. Now let's try to look at what all we are discussing. So this all are the cycles what we have discussed up till now, and now we are discussing this particular cycle, that's what is with the turbofan engine with intercooling and regenerator. So now here this what all we have discussed, that is been represented. Okay, now let's try to look at, you will feel, sir, this intercooler basically is putting advantage in terms of say higher thrust generation, as well as it is improving the work capacity or work output, but we are putting additional amount of fuel, it is not giving that benefit. Then why are we not incorporating only regenerator? What is the need of this intercooler? Yes, it's supposed to be the question to all of us. So why this intercooler is? Just try to understand the logic here. So here, in order to have the effective heat exchange to happen, in order to have effective heating and cooling to happen, what is our requirement? There need to have sufficient temperature difference between these two. Which temperature difference? Say LP turbine exit and HP compressor exit. If we will not be having that sufficient temperature, then it says like it is difficult to achieve the effective heat exchange process. So the purpose of regenerator will not be served if I'll not be incorporating the intercooler. Got the point? So you can understand, I want this point 0.4 as low as possible. I want this 0.7 to be as high as possible. Now the question will come, sir, what is the reason why are we looking for this point to be higher? Basically, this is what is being driven by our HP turbine. We can say turbine entry temperature, that's what is playing important role. This turbine entry temperature for takeoff condition is higher, and up till now what all numericals we have solved for say cruise condition, we have realized the turbine entry temperature, that's what will be lower compared to say takeoff condition, that will be in the range of 300 to 400 K. If that's the reason or that's the condition, what will happen? It shows like if this temperature will be lower, then there is no purpose of incorporating this recuperator. So like you need to be very careful in terms of selecting or designing this cycle as well as this engine. So just realize what is the reason why we are having the combination of intercooler as well as the regenerator. There is a specific reason behind the selection of this device. Okay. Now in Europe, along with what all we were discussing as vital project, parallelly other projects also were running. So this is one of the project, it is called New Aero Engine Core Concept. It's a NUEC project. So if we look at carefully, we are having this as high bypass ratio fan. That's what will be followed by the booster compressor or LP compressor. Here this is representing my intercooler and this is representing HP compressor. Now as we have discussed in this configuration is basically intercool and recuperative core concept. So here we have centrifugal compressor from where the air, that's what is passing through the recuperator and that's what is getting heated up. That heated air that's passing through say combustion chamber, and here we are having turbine. So here if you look at, this is representing the construction. So what all differences we are finding compared to conventional here is in terms of how this say intercooler it is been incorporated. Similarly here if you look at, we are having this as our centrifugal compressor and this is representing our recuperative cycle. Now the question may arise, what is the purpose of centrifugal compressor? So we have discussed this point earlier also, when we are looking for a special kind of configuration where the length of the engine is a constraint, we will be going with say centrifugal kind of configuration. Parallelly, we have discussed the limitations of the centrifugal compressor. Say entry of the flow is axial and exit coming out from this centrifugal compressor is radial. So you need to have a specific device or diffusing device which will be guiding the flow in axial direction. But here it is reverse flow kind of configuration we have for the combustion chamber, and this design it is purposefully been done. Here if you look at, it is using the piping for say recuperative kind of configuration. So let's look at what is happening. So somewhere here if we look at, it says my overall pressure ratio in the range of say 50:1, which is giving say thermal efficiency of some number. By incorporating this concept, we will be able to achieve high thermal efficiency with higher say with lower overall pressure ratio. That's what is the benefit of incorporating this configuration. So research, that's what is going on in terms of development activity with the major objectives as to improve the efficiency by 0.8%, the weight reduction by 10%, and the total losses by 15% in the recuperator. Now let's look at the other configuration. This is other configuration where we are not having say regenerator. Here it is only say intercooler, it is been incorporated. So here in this case, if we look at carefully, this bypass duct, it is not been disturbed. The air, it is being taken out from some stream here for the intercooling purpose. the air which is coming out from the LP compressor, that's what is passing through the intercooler, and that's what is being supplied to HP compressor. If you look at carefully, this HP compressor, what we are looking for, they are having more number of stages. So, HP compressor stages are higher. In this configuration, it is not being incorporated with the recuperator or regenerator, and straightway the exhaust, that's what is going to the atmosphere. Now, this configuration has its own benefit in terms. So, if we compare here, it says we are able to go with the higher overall pressure ratio. At the same time, because of this intercooling, we will be having thermal efficiency, that's what will be improved compared to the conventional case, but obvious it is lower than that of the intercooled recuperative kind of configuration. So, here in this case, it says since my air it is being cooled, that's what will be helpful in order to cool my HP turbine blades. So, the bleeding requirement, that's what will be reduced. There are many benefits which they have explored with, and the objectives for this demonstration, it is to 4% reduction in specific fuel consumption, 16% reduction in say NOx emission by incorporating this intercooling, and at the same time it shows the overall improvement in terms of the engine. Here if we look at carefully, this is representing say recuperative implementation. So this kind of engines, they are also under development activity. Now let's look at what all we have discussed in terms of the configurations. Now there is one more concept, that's what is going on. It is in terms of incorporating the different kind of configuration. Here if we look at, we are having the construction to be different. Okay, in this if we look at carefully, this intercooler, it is being placed in this region, and it is with the specific reason where it says by using this intercooling, we will be able to cool down the air which is enter inside the combustion chamber, and by doing so we will be moving towards the lean combustion. That's what will be helping in terms of reduction of NOx as well as the specific fuel consumption. And here in this case, there is a special requirement of active cooling system. At the same time, it is also been implemented with say active clearance control for HP compressor, active surge control. So different kind of possibilities people they are exploring, because as we have discussed earlier, by incorporating intercooler and regenerator, we are having the issues in terms of weight, complexity of the engine, as well as say your flight safety and the cost. So specific fuel consumption, that's what is of major target. It says there is an improvement of specific fuel consumption, as well as because of weight reduction, since we are not having say complex cooling system, this is giving the benefit. Now there is one more configuration what they have explored with. It is, we have discussed with the counter rotating fan kind of configuration, and here in order to move with a special kind of reduction of say number of stages, special kind of configuration it is been selected. They are expecting per stage pressure rise to be very high in order to reduce the HP compressor stages. Okay, and that's what is giving a new kind of inclination, where we will be having say new concept of say casing treatment, aspiration, air injection, all those possibilities they are being explored. So we will be getting the benefit in terms of counter rotating fan configuration with this kind of additional devices. When we are incorporating this additional devices for the control, it is but obvious it is making our system to be more complex, and it required a lot of attention. So these are the projects what European Union they are exploring currently for a special purpose for say commercial engines, as well as they have focused on their military purpose also. So let's try to understand what all we are discussing currently. So we have our engine requirement, that's what is for say turbofan engine, At the same time, say large turbofan engine, turbosaft engine, turboprop engine, small turboprop engine. These are the requirements of current era. Okay, we are looking for this kind of configuration. They are having the specialized applications where you can say application for commercial purpose, applications for the UAV, application for the cruise missile, even for the military purpose. And in this we are having say heat exchanger. That's what they have implemented, what we have discussed for intercooling and recuperative kind of configuration, where we are having the recuperator. They are of different configuration along with the intercooler, and they have potential benefits. If we look at carefully, this is what we have discussed currently is in terms of large intercooler and recuperated turbofan engine, where our target is to reduce the emission, fuel burn and noise. At the same time, there are special requirement if we look at for turbosaft engine, where we are looking for the reduction of IR signature. So based on the requirement, people they are exploring different kind of configuration which are possible for this kind of engines. So here let's try to look at what all are the challenges for this turbofan engine with intercooling and regenerator. So if we look at carefully, by incorporating this intercooling and regenerator, we say we are basically increasing the complexity of the design, because it is increasing the design, manufacturing and maintenance complexity. It required higher development and operational cost. Because of this additional devices, it is increase in the weight of the engine. We are having say overall weight increase, as well as we will be having say future balance issue with this kind of configuration. Payload capacity also will be reduced because the engine itself has very high weight. Engineering challenges is in terms of effective heat transfer that need to be done with the minimum pressure loss, and that's what is required to be performed under different operating conditions. That's what is very challenging. Thermal management is a big issue for this kind of configurations. In terms of reliability and maintenance, so if we look at the heat exchanger device, let me share you here the devices what we are using, say in terms of say intercooler as well as regenerator. Say for this project, Fiat has involved because they are having their involvement, special involvement for say radiator. They have expertise for development of specialized coolant, say cooling circuits, and they have helped a lot for this kind of configuration. Now reliability and availability of this intercooling and regenerator, it is very much essential for uninterrupted aircraft operation. When we are incorporating this kind of configuration, always we need to go with the testing, certification, regulation approval, and that's what is increasing the more complexity. And in terms of performance, as we have discussed, we need to play or we need to compromise somewhere in terms of our expectation under specialized say flight conditions and operations. And cost, if we configure, it is highly cost in terms of manufacturing as well as maintenance, and that's what is need to be assessed carefully. The integration of such devices in engine, it is very challenging. Suppose if we are looking for say retrofitting, that also makes this device to be incorporated to be very challenging. And development activity and optimization of this kind of system, it is very time consuming, and it requires special kind of research and testing and certification. So in overall, if we look at this configuration, what all we are discussing in terms of say intercooling and regenerator, they are more promising for the land based power plant. But when we are talking about the application for the aero engines, where we have a lot of constraints in terms of size, weight, operation issue, safety, certification, that's where it's a long way to go. But still, lot of efforts they are being put on by European Union in order to incorporate this kind of configuration for the future engines. So here we are stopping with, we will be discussing about say how do we do the cycle analysis for this special kind of engine configuration in next lecture. Thank you very much.